The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, good morning, wherever you are in the country. It's Mark from SolidCAM. We'll be doing our next day of SolidCAM Live. With me, I have Kevin. Hey, Kevin, how you doing?
Hey, guys. Good.
So first, got to apologize for yesterday. I think there was a global issue with GoToMeeting, GoToWebinar, so couldn't get it started yesterday. And by the time we figured it out, I think it was too late. So the topic we were going to cover yesterday, we'll cover today. And that is one of the, I guess it's either a lingering question from the last session, or I guess you could kind of consider it a new topic for today. And that is a really common training question. With all the toolpaths we have in the list, how do you choose which one to use when? And that kind of a question, that's perfect for a training session or a really long-winded basically a longer presentation. And there's a lot of KevCam videos on that sort of topic, when to use one versus the other and that sort of thing. So Kevin always does a great job with his fully fleshed out deep dive channel on that. So what I want to do here is just with the 30 minutes we have, we'll focus on just the one toolpath that seems to get the most questions, and that is HSM. Because HSM has so many different technologies in it, just one toolpath, but it seems to almost be like a bunch of toolpaths in one. Let's focus on just that. And that's this same part we've been looking at. And I use this during demonstrations and training to show each type of technology in HSM. So if we start from the top, if I just open this up, what I'm referring to is everything listed in here. So each one of these is a technology for HSM, but the parameters, all the input you put in there is the same for each one. You're either giving it a step over, step down, depending on what type of technology it is. It is all of them are HSM, so it's a solid-based toolpath. So right off the bat, the first question would be HSS versus HSM. And my rule of thumb is if I have a part that has many different directions, many different little tiny surfaces, it's more of a solid as a whole that I'm trying to machine, I'll use HSM because it's solid-based. I don't have to choose all those tiny little surfaces that we have in here. Whereas HSS, kind of like we talked about earlier this week, is much more targeted. So I can actually tell it that specific surface is what I like to machine, and I can give it a direction and a parallel to curve or whatever I want to do. Between HSS and HSM, they have the same technologies. You can do parallel to something, morph between something, only do verticals, only do horizontal. There's different parameters you can set, but between HSS and HSM, one is surface-based, that's HSS, that's the surface, and then HSM is the solid-based one. So I always think of it as the model. So you're using the target model as the geometry for an HSM toolpath. Does that sound fair, Kevin? Would you agree that's kind of the rule of thumb?
Yep, absolutely.
You can, like I said, but you can get almost the exact same toolpath between the two. It's just that with a solid-based one, you have to give it a working area to limit the travel of the tool. Whereas in HSS, the surface itself gives us that boundary area. But let's do a deep dive as much as we can in HSM. So this one right here is our horizontal, I believe it is. Let me just open this back up here so we can take a look. Horizontal machining. So horizontal machining, you'll notice that it only does the flat faces of this part. And that's because this is only horizontal faces. And if you go to passes, it only gives you a offset or a step over. There's nothing here controlling how to step down across something. It's literally just for finishing those faces. We go to the next one. This is the opposite of that. This is constant Z, where it focuses only on the non-horizontal faces. So you'll notice a lot of the curved faces on this part, they're getting a lot of step over. And then when it gets to the flat faces, you can see there's nothing on there. Another thing you'll also notice is some of these curved faces that become a little tangent with those flat faces, you're seeing less and less toolpaths as you go along there. There's two things going on there. One, it's becoming almost horizontal. But two, we give it in this toolpath a step down. So somewhere along that tangency there, that is becoming less than a 10th step. So it would not add that step there. So that is constant Z. So between those two, you would switch from your flat end mill to your ball end mill, your bull end mill, whatever tooling you want to use for the different surfaces to get the different finishing. And you can give it different step downs as well. Obviously, maybe when you're doing a vertical, you might want to use on a curvature, maybe a tighter step over, or if it's a vertical wall, you want to do a larger step over, use more of a side of a tool or something like that. Whereas the horizontal, you're going to want to do your step overs based off of the tooling you chose as well. So that gives you a way to kind of break it up to only horizontals, only verticals, or only curved, or however you want to think about it. The next is linear. And this one is a very easy one to program because basically, again, your solid is your geometry. So I'm basically telling it to just go zigzagging back and forth across the solid. And you give it a step over. The direction is very similar to what you would see in HSS, HSM, anything where you're actually just giving it kind of a linear direction. You'll see this also with pocketing and the hatch option because you actually have to just give it an angle. And usually the angle is an angle off the x-axis. So that's why when this is set to 90, it's going in the y direction. But I've applied this to the overall part. Now, I usually use this particular option in HSM to highlight that maybe you don't want to apply one HSM technology to the entire part because this is a great toolpath because it's really simple. I just tell it which direction I want to go. But because of all the curvature and the changes direction on this part, there are portions of it where it's not going to get the best finish because of the linear nature of that toolpath. It might look good on this side, but then this starts to fail because that is a step over along the part.
Yeah,
so
and if you guys could think of as linear is set up, really shines on from 0 to 45 degree surfaces, where constant Z really shines on 45 to 90 degree.
That's an excellent point because it actually leads me to kind of step back a bit to constant Z, or sorry, constant Z. Got to remember my audience. Constant Z, hybrid Z. In hybrid Z, you actually get the ability to add a little bit of a step over as well. So it kind of goes with what Kevin was talking about. This one, you don't get an angle limit, whereas when you get to add your constant Z with linear, this is where, like Kevin was saying, one benefits at a certain angle range and another benefits at another angle range. So in the combined constant Z with those two that we already talked about, you can put the angle limits in there and get your benefit. You're getting your optimal angles depending on how you'd like to address it with your particular tool. Okay, let me exit out of here. I do not want to save. Okay, so we talked about linear. Let's go to the next one. Now, the next one is called radial machining. And it kind of goes back to what I just talked about with linear. Sometimes you don't want to apply one technology to the entire part. So in the toolpath, you actually get the ability to add a working area or a constraint boundary in this case. And for this one, I've constrained it to just this dish feature right here. That's because radial machining, we go to the passive section, allows me to choose the center of a radial pattern, a minimum and a maximum radius. And then when I generate the toolpath, it looks like that. Kind of a star pattern, bike spoke, however you want to refer to that. It's basically just zigzagging in and out from that radial pattern, that radial dish there. And you can imagine that this looks like a good toolpath here to finish this dish shape. But for an overall part, maybe a square part like this with all these different angles and curvature, you probably don't want to zigzag back and forth to a center point. So you choose these technologies based off the finish you're looking for. This is a finishing toolpath. So you look at where you want your scallops to flow. You see what kind of tool you're using if it fits with the shape that you're trying to generate. Okay, and the same is for spiral. Spiral toolpath, if we look at this from the top view, I can assign a center, I can assign a minimum maximum radius, and what I'm doing with spiral machining is I'm basically getting it to drape this spiraling toolpath, starting from inside going out or outside going in, and I drape it in 3D with a offset and a step over. So that is perfect for any kind of shape like this or these other bosses, not so much for the entire solid. Morph machining is again another one that you might want to use with some constraints. This one here, if we take a look at it, Morph machining has the added option here of dry boundaries. So I basically tell it, let me just hide the wireframe here. So I tell it from that curve on that surface to that curve with a little bit of a bend you can see there. It actually generates the toolpath starting from one side being parallel and morphs it to get the other side. If we take a look at that, you can see that it starts to develop the bend, and then as it gets to the end, it's actually parallel to that bend in that curve there. Again, we're finishing this part. we probably want to get a nice finish. We want the flow to go along there. In this case, there's along. If I chose some curves where I wanted to actually go across, maybe perpendicular to that curve, I can do an across. And the passes are a step over. So again, it drapes that offset, that step over pattern onto the 3D surface, but it's driven by these two boundaries here, starting on one side and going to the other side. Not to say that you can't do this on the entire part, but you're looking to choose one side or another side and blend it. Sometimes that's not going to work on something that changes a lot of different directions here. Offset cutting. So this one is the idea that you choose one curve. In this case, if we kind of zoom in here, we choose one curve we want to stay parallel to, and we stay parallel to it as much as we can as we travel across the surface. So if you ever used HSS, this one's very similar to parallel to curve in HSS. Whereas again, in terms of geometry, it's all based on the target. But in my constraint area, I'm doing the entire target as well, but I'm only offsetting from one chain. So if I just show that chain, it's just that guy right there. So because it's that limitation right there, I just want to go from there to there, and I'm stepping over by an offset value of about 450 thou. So 450 thou parallel to that line is where I'm going to travel. That's pretty much about here. And then I'm stepping over to it by 10 thou. So it's very similar to parallel to curve, or if you're looking at it as maybe just one of the 2.5D toolpaths, like in parallel, when you do a clear offset in parallel as well. So that is the 450 limit right there. But as it gets a little further in this direction, the 450 limit is probably around there, parallel to that final point. So that's why it begins to kind of curve around there, because it is a parallel offset. So it curves along here because that distance right there is also 450. Okay, let's exit out of there. Now, boundary machining. Boundary machining, I don't have a good representation of it here, but there is actually a video, either there was a KevCam or one of my short videos on this, but this is actually a good way to do some engraving on a 3D model. So you can do 3D, sorry, go ahead.
Or deburring.
Or deburring. This one is perfect for deburring because you're really just choosing the outside edge there and you can deburr it. So this is one way to do, actually there was a good video that, that we did on a really oddball part where we used this with some gouge checking to use a uniquely shaped tool to deburr or to make this certain shape that otherwise would not be, the toolpath would not be generated just on the geometry alone. And that's only because this guy follows a particular boundary and then it offsets it from the surface. So the boundary on this guy, if we open this up, is the automatically generated one, I believe. And that's just the outside of the part. So it takes that sketch there and projects it onto the solid. In this case, it's just the outside edge. But if we look at the toolpath, it actually projected it and followed the edges of the solid. So it's a good way to deburr the outside of the part, or, and I think I had an option of it here. If not, there's another video that shows it, where one of the drive boundaries could literally just be text or some sort of image. And then you can actually use that, driving it by the center of the tool, to almost engrave on a 3D solid, rather than choosing all the individual surfaces. So again, it goes back to that sort of idea of, if you have one surface or a large set of surfaces to choose, pretty easy. You can use HSS, you can use 3D engraving. If you come into HSM, it's solid based. So you can choose the solid faces for that. What about a sketch circle? Yes, you can easily do a sketch circle as well. Maybe a good example of that would be, let's go to the drive boundary, created manually. And let's see if I can find that circle that we had before. So there's my sketch circle. Save and calculate. From the top view, it's the sketch circle. Rotate that around. It drapes the circle on the part. And you can see it actually doesn't fully drape it because there is some gouge checking going on there. So it realizes that it should probably just step away from the wall in order to follow that circle. Is that what you're looking for, Jake? That's the one on the part. Yeah. Yep, there we go. So there you go. So you just choose any kind of sketch any kind of geometry that you're able to select in there, and it just projects it on there. So boundary machining, I probably would have called it projection, but yeah.
Yep.
Yeah, so there we go. Okay, so the next ones are a little more specialized. This one is rest machining. So anytime you hear the word rest in SolidCAM, you're pretty much talking about what was left over. So let's open this up. This one is unique in that because it is a rest machining operation, it has an option here for reference tool. And that's just basically what the previous tool was. So right now, the reference tool was a 3/8 tool, but in this toolpath, I'm using the 1/8 tool. So whatever was left behind by the previous tool. On this part, it's got some sharp edges here, sharp corners, so that automatically would trigger any kind of rest milling operation. This one over here is probably just too tight of a radius for the 3/8 tool, sorry, the 3/16 tool to get in. So the 1/8 tool can fit in there. And then in terms of passes, it's always looking for the bitangency angle. So the angle made by the two surfaces coming in contact with the tool. And then you give it a step down, a step over. And if you need to, you give it a depth of cut as well, because it does recognize that there's probably some extra material. And I think there was one other thing here. I wanted to talk about that. Let's see. Any idea, Kevin? I'm trying to remember here. How does it know how much to feather out to do that?
Well, it's going to feather out as much as the remaining stock is there.
Ah, okay. Yeah, I guess so. So this is
that step over. Yeah, that step over will just control how much of a scallop we're going to be having there.
Okay, perfect. So let's exit out of here. And the next couple of ones are the constant step over toolpath. So let's do this one here. It's for the entire part. So what you get with this one is you get from the outside edge, basically a constant step over from whatever drive boundary you select. So in this case, the drive boundary and the constraint boundary are the same. So it's starting off from that rectangular outside. You can see that it begins to make these corners here as it steps over. And then as it tends to collapse on itself, you get these kind of like end areas, or you get the center area. This toolpath, the direction of this toolpath is fully driven by the constraint boundary, or sorry, the drive boundary. So you can see here, it's actually the same in this case. So from that rectangle, it's offsetting its way inwards. And if you look at your passes, even though it's moving up and down, you actually give it a separate horizontal and vertical step over. So I often say to people, if you're not sure which toolpath to use, you can start with this one because it goes in all different directions. It might be a longer cycle time, but you will definitely get all the little nooks and crannies that you're looking for in your toolpath.
And the cool thing with a lot of pretty much all the HSM operations is you guys can set up, you can see on the screen right now over on the right hand side where the angle range. So maybe if Mark didn't want it to touch anything that has a vertical, straight vertical wall, he could change that over to 88 degrees and then it would stay away from any vertical walls that are there. So every HSM operation has this. So you guys can limit. So maybe you want to stay away from any flat surfaces. You can start it off as 20 degrees or 10 degrees, and it will stay away from anything that is flat.
I just changed it to 2 degrees because then anything perfectly flat is going to be ignored. And we'll just generate that real quick here while we're looking at the questions. So you need to specify the previous tool properties in a rest machining operation because it's working, it's calculating what the previous tool could not. So this one's not actually recognizing the updated stock, unless I'm incorrect on that.
Nope, you're correct. Yep.
I'm correct. So this one is not a stock recognition toolpath. You'll get that sort of functionality with something like 3D machining, and I believe in HSR as well. I think we've added that to HSR, but in HSM, you're really just looking to finish what the previous tool did not finish. So there's no stock recognition there. That's why you have to tell it the previous tool size, and then you give it obviously your current tool size, and it just does the calculation based off that. So that's kind of why I was asking the question to Kevin of how does it know to feather out? It doesn't know how much material is there. It just knows that if a certain size of tool was previously there, then it already has a certain corner rad, and then it just works its way machining that corner rad mathematically, not working off of updated stock. So the calculation is done. You can see because I told it to do it from 2 degrees to 90 degrees, it ignored all the flat faces.
And this
so exactly like Kevin was talking about.
Yeah, this works great too because like When Mark, in his first operation, he told it to do horizontal. So anything that had a flat floor would be machined off with a flat end mill. Then what he could do at this point is come back and now put his 2 degrees in here. And now this toolpath will come and clean up any of those 3D surfaces using a ball end mill and not a flat end mill.
Yep.
So this is the toolpath that I would say gets used a ton. I mean, if you guys were to ask, you know, what's the most common ones that we use in HSM, this would be one that is very commonly used in HSM.
Yeah, exactly. I mean, that's why I say usually that's the one I recommend to people first, because it's probably just the easiest one. To answer your next question, Jake, is the dry boundary actually a boundary, or could you use geometry that's internal to your constraint boundary? Let's open this guy up, and we'll take a look at that exact scenario. So in my constraint boundary, actually, let me do my dry boundary here. Yeah, okay, dry boundary. Let's change the dry boundary here to automatic. So my dry boundary is the rectangle. So I'm going to do an offset off of that rectangle, similar to what we had with the toolpath we were just looking at. But I'm going to constrain it to within this circle, the circle we were looking at before. If I do a save and calculate on that, if the dry boundary and the constraint boundary were the same, I would get that nice circular looking spiraling pattern. But because this guy is using the, for whatever reason, didn't want to calculate, it would actually trim the toolpath to within that constraint boundary. Is that a fair description there, Kevin?
Yep. It would want to stay internal to that. So you'll see down at the bottom where it says boundary tool. So we can stay centered to that boundary. We can go outside of that boundary by doing external, or we can tell it to stay completely internal to that boundary as well. And we could just have too big of an end mill to fit in that boundary right now.
That's probably what's going on there, yeah. So let me just switch these back to where they were. So the drive boundary, let's put that back to created manually. I think it was that guy there.
So kind of how it works is you can get your shape from the boundary, but keep it contained to, so the shape of the toolpath is following that outside boundary, but keep it contained to a certain area.
Exactly. All right, so we did those two. Let's get to, again, these ones are getting a little more specialized. This would look kind of like arrest milling, but it's actually called parallel pencil. And what it is it's still using that bitangency angle. So if we open this up, it's still looking at the angle made by the tool, 2 contact points, one on one surface, one on the other, to see what that bitangency angle would be. You're still getting your ability to do step over and step down. You're actually, in this case, giving it the ability to tell it how many steps over as well. Because what you're actually trying to do is you are trying to drive the feathering yourself there. There's actually 2 pencil milling technologies in HSM. There's parallel pencil, where it gives you this step over. And then there's just the simple pencil, where it finds the bitangency angle, and it just takes your ball end mill, and it just kind of does a 1 pass down the center of what that bitangency angle would be. So again, just kind of working on the tight areas. And if you take a look at the model, it's all the really tight corners.
And where this also helps out too is if you have a ball end mill that is size on size of the radius of what you're trying to cut. So it will just follow along, leaving that 1, 2, 3, however many cuts you tell it to do, to come in there and just clean up that small little radius.
Perfect. I mean, these are finishing toolpaths, and a lot of times you don't want to take too much time to figure out how to get in there if, like Kevin says, it's on size. You just go in there, clean it up, and you're done. And then the last one is 3D constant offset, I think it's called. Let me just see what the proper terminology on this one is. Yep. 3D corner offset. This one, don't really know how to describe this one. Because I know you did a KevCam on this. What's the difference between this one and the other one?
This one is a very powerful one. So what it's doing is it's looking at the curvature of your part, and it's trying to keep the lines in curve with your part lines that are already in there. So as it kind of goes through, and this part probably isn't the best example of it, but like in that dish in there, it's trying to do the dish out, and like where the flat area is right above that bowl, it's trying to follow that V line in there. So it's taking and looking at all the geometry that is there, and it's trying to keep the flow lines, I guess you would say, keeping so it's flowing more along with the geometry itself. So if we did 3D constant step over, it is just 3D constantly stepping over and working its way out or working its way in. Where this one is doing is it's doing the exact same thing, but it's looking at the physical geometry itself. So as it starts getting from a square up to a circle, it starts morphing its way over from that square to a circle. If that makes sense.
I guess that's why it's called corner offset, and then this one is just step over.
Yep. So that's between 3D constant step over and the 3D corner offset are my two favorite HSM operations. It's kind of like hitting the easy button, and that those two tool paths, majority of the time, I mean, we're all dependent on what we're machining here, but majority of the time those are the ones that are my go-to tool paths using for HSM. And you'll get a real nice finish using that 3D corner offset, just because it's flowing more with the physical geometry of the part.
Because that's usually what we're looking for on finish, right? We want to get that kind of matching the geometry. Yeah. Okay, so that's all of the HSMs. Now I know coming up probably is the KevCam on the new HSM.
Yep.
If I'm not mistaken. Yeah, so look out for that. I'm not sure where that is on the schedule, but there is a version of HSM that was introduced in 2019 or 2020. I can't remember now, but called Turbo HSM. And it has a lot of the same functionality. Obviously, Kevin's going to go and do a deep dive, but it is a really powerful version of this toolpath. And it's got a lot of the same functionality, but it also has a few new tweaks to it because of what's behind the way that thing works. So it's actually pretty interesting. But I think we're at the end of the half hour, looks like.
Yeah, quick.
So like we always say, this is a daily thing that we're doing up until May 1st. And this is in response to maybe a lot of people have some time to take a look at our stuff. They're looking at maybe some more training. So in that view, if you're interested in getting some live training, one-on-one training, contact your local sales guy. You can even call us directly. We can schedule you for some online training with myself, Kevin, Greg, all the guys on the team. And we can match our training schedules with yours. Whenever you're free, whenever you need the help, give us a call, as well as the main tech line. That's always available to you. Anytime you need help, just give us a call there. Let me put my email in the chat, because I know you guys probably already have Kevin's email, but you can have my email as well. And if I could spell, there it is. So any other topics you want covered in this daily training session, let me know. We'll put it on the calendar for the training sessions as well, and we can cover that in the half-hour daily thing we're doing. I appreciate you guys showing up. I can say probably on behalf of Kevin and myself, I really enjoyed doing this. I look forward to seeing you guys on Monday. Stay safe. If you guys are doing any essential work, on behalf of myself and everybody, thank you for your essential work. We'll talk to you guys next week.
All right, see you guys.